So good morning, DDD. Thank you all for coming this early morning. I just want to mention a few, I have some special announcements for all of you. Just to mention, we have some special guests, and that include a project that is called She Space. And this is 17 high school girls that will present their research on climate change on posters, and this will be during the poster session. So you are all invited to the poster session at 12:30 to 2:30 with two locations, one She Space and the other one is the other students and researchers. So during the poster session, we'll again have open campus tours. So if you want to see our labs, and you are welcome, and also to come see there is also two things that will be presented. Also, we'll have a movie here about a very new and I think, very good movie that Professor Simon Barak did about our institute, and also to see the vertical field container where we grow plants. The second thing I want to say is today we have sessions here and in another location, which is the Research and Development Center in Ramat Negev, which is 20 minutes from here. We will have shuttles going all the time back and forth. So anytime, so please look at the program and look. In Ramat Negev, today, we will have 5 events. The first one will be agrovoltaics, a session about agrovoltaics. And after this talk, there is a bus shuttle going to the R&D. The second one after that, and if you want to come back after that session, so there are shuttles all the time. So you want to go one session, you could go back and forth. Crop nutrition. The third one at 5 p.m. will be about the MENA, the Middle East North Africa Corporation, which will have Professor Farid Lekaja, and Professor Abdelrani Khabani from Morocco, and Professor Noam Weisbo, the head of the Institutes of Desert Research and a Desert Tech representative. In addition, we'll have our dinner today, will be in the R&D. So after all sessions, if you stay here, we will have shuttles going to the R&D, okay, to Ramat Negev, which is 20 minutes from here. Okay, this is also sponsored partially by the Council of Ramat Negev. So there won't be dinner here, okay? Dinners and activities in the evening after are all in Ramat Negev, okay? We'll have shuttles going there. After dinner, 8:30, they'll have shuttles coming back, or we also will have a very special presentation of a movie that's called The Dead Sea Guardians. It's really a special experience to see the movie, and it will be together with a panel with Professor Jack Gilron and the creators of the movie. The movie shows 3 individuals, an Israeli, a Jordanian, and a Palestinian, that do everything they can to save the Dead Sea that is really dying, and swim across from Israel to Jordan in the Dead Sea. And it will be a 55-minute show, so if you want to see it, you are welcome to come and see the movie. It's 55 minutes, 8:30. If you want to see the Iran-USA game or the England game, so there is shuttles back, okay, 8:30. So the movie is very good. I really recommend it, okay? So this is regarding the shuttles. We have also tomorrow 8 tours. So if you didn't register, you can register to the tours. Okay? Some tours are full and some not. So if you are in the agriculture to the Dead Sea, please anyhow go to the registrar and make sure you're registered, okay? That we will have a space because they're quite full. But the other, we have very, very great tours from Bedouins, Dead Sea, floods, viticulture, and I'm probably missing energy, water. So really, the tours are recommended. So we really... I can recommend only for you to come. The 2 last things. So tomorrow we are going to the tours here on campus. If you're not going to the tours, we'll have the Ben Gurion Day, where the Israeli government, including president, prime minister, and different ministers and all kinds of VIPs will be coming to the gravesite, and it will be a little bit high-level security. Okay, so if you are not going to the tours, maybe go with your passport or something, okay? So just make sure, that's all. Thursday, I recommend there is in the morning activity of, I'm not how to say, bird watching or bird even not watching, banding or, yeah, what? Ringing, sorry. Okay, so these are my announcements. So if you have any questions, I'm always free to answer. I'll be happy to answer. I'm very, very proud and glad to have our next keynote speaker, Professor Osvaldo Sala, who was he's sponsored by the Goldman Sonnenfeld School for Sustainability and Climate Change that helped us bring Professor Osvaldo Sala, who will talk about effects of climate change on drylands. And the floor is yours. Thank you very much.
Thank you very much for this opportunity to be here, and that also the opportunity to have all these informal conversations with all of you. And a special thanks to the newly formed School of Sustainability for sponsoring my trip here. That is, again, it's a great opportunity. So thank you very much. And I think the School of Sustainability is a great opportunity and a great opportunity for collaboration with Arizona State University. So today I'm going to talk about the effects of climate change on drylands, and I'm going to focus primarily on precipitation for things that are obvious to all of you. Precipitation and changes in precipitation is what drives drylands. But I'm going to be focusing on two aspects of that: changes in the amount of precipitation and changes in the variability of precipitation. And of course, questions are welcome when I'm talking and after I talk or anytime. So the first thing is I'm going to be talking about two dimensions of climate change. Changes in the amount of precipitation, that, as you can imagine, and also a dimension of the climate change that is changes in the variability of precipitation. And also you can imagine that this also could be potentially very important. And I'm going to try to separate the two. So just to give you some sort of a personal impression, I think it's very easy for us to compare two jobs, one that makes 100 and one that offers you 120. The 120 is better than the 100. But think about two jobs that offer you the same amount, but one pays you only in even years, another one pays you every year. And the one that pays you in even years only pays you double. So that's give you a sense of what is, from a human perspective, what it would be the effect of changes in variability, even though the amount that you get is the same. And so the first, I'm going to show you this figure. This is a figure for the US, and this is an aridity index called the Standardized Precipitation Evapotranspiration Index, SPEI. I'm not going to spend any time explaining that, but you can imagine it's sort of a ratio between amount of precipitation and temperature. It's a little bit more complicated. But this is the rate of change in the last 100 years in SPEI, changes in SPEI per decade. And what I want to show, this is the US, and you can imagine this is the more mesic part. There's a sharp precipitation gradient from the east coast to the west coast, and you see that around this is the 100 meridian. In all the eastern part, the mesic part of the US and the mesic part of North America, during the past 100 years became wetter. And all the western part of the US get drier. And if you look at it, the hottest and driest part of the country got even driest, okay? And so this is for the US. This is for the world, one of the IPCC scenarios. And you see this is changes in precipitation. Now we have no temperature. And you see that the northern part of North America is going to get wetter. And the southern part of North America is going to get drier. So you see the same pattern that I was showing you in the previous. We're going from data from the past to going modeling into the next 100 years. So this is some of the IPCC results comparing the difference between the 2100 to the 1970s. So this is what we are seeing. And this is, so we went from the US to North America. This is the world. And you see there are parts of the world that are getting significantly drier. Here where we are is going to get particularly drier. And parts of the world are going to get wet. So I used 3 slides to tell you that the world is going to get drier and wetter. Not very exciting, but it's not all going to get necessarily drier. And so this is one of the dimensions, the dimension about amount of precipitation. So though this is, they do the same sequence with the coefficient of variation of that index, the SPEI, the aridity index. And these are changes per decade in the aridity index. And you see that the same pattern happens. The eastern part of the US is getting progressively less variable. And the western part, the drier part, is getting progressively more variable. So what if you use my first slide, my fourth slide, you see that the drier part of the world, or the drier part of the US, is not only getting drier, but more variable. And the wetter part is getting wetter and less variable. And this is data from the last century in the US. So now, this is another IPCC results, and this is looking at the future. So this is, in the x-axis we have time, this is the past, this is variability in the standard deviation of number of dry days. So they count the number, the length of the period without rainfall per year, and this is the standard deviation of that variable. And so you see this is the past record, and these are 3 IPCC global change models. And you see that most of them predict an increase in variability. So basically, what we are saying is that there is going to be parts of the world, they're going to get drier, parts of them get wetter, but all over, there's going to be increase in variability. All right? So this is I'm using many slides to tell you that very simple message. And maybe my whole talk may fit in 5 minutes, but so we are okay with that. Okay. So now let me move I want to share with you our scientific approach to tackling those issues. And for that, we use an array, a set of different approaches. So this is our puzzle. We're trying to understand what is going to happen with changes in amount and changes in variability of precipitation in drylands. And for that, I'm going to present 4 types of data. When we're going to report on observations. So observations have the ability, they are not very expensive to do, and they cover a lot of space and time, and they are in sharp contrast with experiments. Experiments is when we manipulate precipitation, manipulate the amount, manipulate the variability. Experiments are, in that sense, unique. Experiments is the only way that we have to assess cause-effect relationship. The only way to know how much variability affects something is when you modify only variability. Don't modify temperature, don't modify seasonality. So experiments are unique, but at the same time are very expensive. You only can have one and only last 2 years or 3 years. So it's very difficult to extrapolate. So I'm going to argue that the two of them sort of complement each other. Finally, I'm going to share with you some results of modeling. So these are mathematical models that allow us to something that is very interesting, because with models, it's very cheap to go into the future, into different parameters that never existed. So we can look at things that we cannot do with observations. We can do things that we cannot do with experiments. But they complement each other. And finally, I'm going to show you some data mining. There are a lot of data, and data are becoming more and more available, since most of our funding agencies, journals are all asking us to make data available to. So hopefully I'm going to convince you that working with the four approaches together give us a different perspective. And so the first part of the talk is going to be talking about precipitation amount, changes in amount. And I'm going to be focusing on four specific questions. So the first one is, how does duration of altered precipitation regime affect the response? So in other words, it's the same to have a 1-year drought or have a 5-year drought or a 10-year drought. What it matters is the intensity of the drought or the duration of the drought. Doesn't matter. And also, when we talk about precipitation amount, we think about both drought and very wet conditions. Are they both symmetrical? So if a 100 millimeter decrease in precipitation over the mean has the same but the opposite effect that a 100 millimeter increase in precipitation. That's what I call symmetry. If there was symmetry in the response, that would be kind of cool, because then we only have to study half of the relationship, isn't it? And my third question is about plant species response. And most of us are ecologists, and so the question is, do all plant species and functional groups respond similarly? It would be great if all of them do. Just study one plant and species and we're done. And the fourth question is the interaction between the response of species and the effect of climate change. So if species do respond differently, how that they amplify or reduce the effect of climate change. So now I'm going to go very quickly through 4 slides that all have the same structure. This is basically the hypothesis that all of them have time here, and here is some sort of an ecosystem response variable that I usually tend to think about primary production, growth of vegetation. And so all of them are going to have a black line that explains ambient. This is a drought experiment, and this is an increase in precipitation, an irrigation experiment. So what we are saying here is that there's no effect of time. So an increase in precipitation increases immediately production and stays. So in a drought, that's the same. And in the bottom, you're going to see some sort of a very simple linear models, where in this case, precipitation is the only thing that matters. Time doesn't. In the next one, it's the same, but we are arguing an alternative hypothesis that matters. The duration matters. That throughout the years of duration of either this drought or deluge, English doesn't have a good word for the opposite of drought, but I'm using deluge, but that's what we have. And so here we're seeing that through time, the effect of either increasing or decreasing precipitation increases the effect on the ecosystem. And then we have some sort of evidence. So in the southwest of the United States, there was this paper by Deborah Peters that looked at precipitation from 1994 and then you see that these last 5 years happened to be from 2004 to 2008. There were some wet years. And I think and you see that the mean of these 5 years is higher than the mean of the long-term mean. That's okay. But what is interesting is that what she reported is the effect on primary production. So this this is the primary production before those 5 years, and this is during those 5 years. So what it sort of is suggesting is that during those 5 years, the production didn't increase immediately, so it took some time. You see that there is a positive relationship with time. That is sort of give us a suggestion that time may matter. The third option is that there is some sort of an acclimation. So it could be that time matters for a while, but then after some time, the effect of precipitation. And I would think about going outside climate, but there's a paper that always was important in my thinking, that they warm the temperate forest in Massachusetts, and they warm the soil. I think Jerry Melillo was the main author. And then, of course, they found an increase in soil respiration. And what did he do? Publish it in Nature. So said soil warming is going to increase soil respiration. And 10 years later, they published another paper in Nature saying it doesn't happen anymore. and in retrospect, it makes sense because so there are examples in nature of this, what I call acclimation. And in the case of the soil respiration was basically they ran out of labeled carbon to burn with the higher, with the warm soils. And so finally is that we are talking about here one ecosystem could be primary production, but doesn't mean that affects all this, the ecosystem processes are going to do the same thing. And finally, this question that I just alluded at the beginning about the asymmetry. Maybe the response to drought is not the same as the response of wet conditions. So after all this long preface, let me start with an experiment. This is an experiment that is very close to my heart, and I always try to bring it back. It's a 15-year-old rainfall manipulation experiment that there are not very many long-term experiments of manipulating precipitation. And this is just to give you, this is happens in the southwest of the United States, and this is the record. And this, what we had is an increase in precipitation by 80% and a decrease in 80%. Sort of relatively simple, but the reason why I show you the past precipitation is to show those things that look like a very extreme plus and minus 80%. You see they're not that extreme. So you see that in the last, from 1915 to 2005, there were cases in which we naturally embraced that plus minus 80% variability range. So here's an introduction of our experimental site. It's called the Jornada Experimental Range. And it looks like a mix of shrubs and grasses that is located in the southwest of the United States. And it is the northern part of what is called the Chihuahuan Desert that happens most of it in Mexico. And so what we did is this very simple experiment where we have rainout shelters that are acrylic V-shaped shingles that intercept 80% of the incoming precipitation. The water that is collected in these rainout shelters goes into a temporary tank from where it's pumped into an irrigated plot. So that yielded sort of a drought and irrigation. The same, if we intercept 80%, we have plus 80% here. Correct? This is relatively simple. This is a picture in real life of one of our systems. We have plots that are 2.5 by 2.5 and plots that are 2.5 by 5. And we have like 246 of them in the different experiments that I'm going to be talking to you today. This happened to be one of the early ones. This is one of the smaller one of 2.5 by 2.5. We started small. And then here I want to make a small stop in trying to, I'm going to be discussing this experimental design, and this is aimed at most of you who are usually reviewers of our papers and our proposals. And the question that I normally get is this plus 80, minus 80, is this going to happen in the Jornada? And my question is no. This is not the objective of what I'm trying to do. I'm not trying, the objective is to assess the sensitivity to precipitation. No, we're not trying to mirror any particular scenario of climate change. And that, in my mind, that's what I answer in a polite way. But in my heart, it says, it's not very smart trying to predict what do you want me to predict? What is going to happen in 2100? So that means that what happens in 2080 is different, or what climate change model you want? So I think what is most interesting approach is to think that the impact of climate change is the response of two different things. Is the degree of changing climate and the sensitivity of it. How much climate is going to change and how much ecosystems are. And I think we ecologists here, we do the ecosystem sensitivity. And the climate, we let to the modelers who do climate change models. And they change faster than we do. And there are many models and many, so our objective is to look at the sensitivity to, and that is an important part of the response of ecosystems to climate change. And in the impact of precipitation is the same. So the impact of changes in precipitation is a result of changes in precipitation, how much it's going to change, and what is the sensitivity to changes in precipitation. Yeah, so, and still, each time I write a proposal, there's always one or two, each time I write a paper, they ask, these are the conditions in what year? And I don't know, I don't want to do that. So this is our introduction to our experiment. I have 6 or 8 figures that are all the same. So here we always have time, and we always have these same color patterns. The black lines are the controls. In this case, what we have is growing season precipitation. And this is our drought plots, and these are our wet plots. Nothing. And now let me try to show you some of our results. So what we have here is the same color, but instead of having precipitation, we have total above ground net prime production. And I introduced you before that our system is kind of a 50-50 grass shrubs. And so we see that in the first 2 years, this is the control, the ambient conditions. These are the irrigated plots. These are the drought plots. It was like you would expect. You put less water, they grow less. You put more water, they grow more. I think, yeah, that's my grandmother used to tell me that I should water the plants. If not, they don't grow. So it's sort of nothing really new. But we were stubborn and continue doing that. And we see that there is some sort of an acclimation. The drought started, the impact was starting to be severe. And by 3 years, got it pretty stable. But things got a little bit more interesting after 2012. You see there's a decline, rapid decline due to drought. But it was really upsetting is that the drought plots also around 2016 had higher production than the control. And my first reaction was to refuse that, sort of pretend it didn't exist. But there must be some sort of fluke. So, and then I started unpacking this and tried to look at the response of grasses and the response of shrubs. So grasses did sort of what you expected. I'm following on the drought here in 2015. And this is the difference between the control. So I sort of, it was a way of separating the effect of my treatment from the interannual variability. And so nothing is very surprising. And then I look at the shrubs, and the shrubs were really boring. Nothing really happened. So from the beginning of the experiment in 2007 until 2014, my explanation was that the shrubs were not very sensitive to water. But I was sort of disappointed that the drought was always a little bit above the controls and sort of this is maybe variability doing field experiments. And then that's what happened the tragedy happened here. So this is what happened with it. This is our drought plots. It started outproducing much more than the control, more than the irrigated plots. And that was the end of my denial. I couldn't deny this anymore. There was no need for statistics. Pictures were showing that shrubs were thriving in the drought plots, and I didn't know what to say until I found this German word called Schadenfreude. That it's a word that doesn't exist in the English language. I don't know, Hebrew has something like that. But that word means the pleasure that we get, and some German speakers can help me here, is the pleasure that we get from the demise of our enemies. And the best example that it comes to me is when you're driving the highway and somebody passes you, and 5 minutes later you see them with the police stopping them, and you cannot help but getting a smile. In other words, I think why I brought Schadenfreude is that not that shrubs really like drought. What they really love is the demise of their competitors, the grasses. All right? And so this is a structural equation for Schadenfreude. And you can have a structural equation for Schadenfreude. And so this is the effect of precipitation. It has a positive effect on grass production. But the production of grasses has a strong negative effect on shrub production. So what had happened is that the shrubs around 8 to 10 years of drought, they collapse. Yes, that enhanced rapidly the production of shrubs. And so now let me go a step further, go into the mechanism of that. And we put saltwater sensors. They are very tricky. They produce tons of data, very difficult to understand. So here we have shallow water. This is deep water. And this is one growing season. And you see that the black is always the same color pattern. And so you see this is the amount of water in the control. This is the irrigated. This is the drought. You see that the drought is consistently wetter. So what happened is that in the plots that didn't have grasses, in the past, the grasses, when it rained, they have shallow roots, they absorb most of the water, and then there was transpiration. And after 8 years of drought, the grasses disappear, and when it rained, the water penetrated into the soil. Then it rained again, it goes deeper, deeper, until it gets to this layer that the only plants that have access are the shrubs. And that's why the shrubs were thriving. This is the mechanism for the Schadenfreude that I show you in the structural equations. Now here is sort of a mechanism of why it's doing what. And interesting, and this is now we're getting to the part that I'm very excited, is that this is the rain use efficiency. Grams per meter squared per year per millimeters of rainfall. And you see that the control and the irrigated had about the same rain use efficiency and was pretty constant through wet and dry years. This seems to be, but the drought plots that are now, we understand, here started being dominated by shrubs, became much, much more, the rain use efficiency goes through the roof. And now you start seeing it, how the effect of something that we started as climate change is now upset by the indirect effects of species composition. So, yes. And so this is what happens. We have the same rain use efficiency here and the growing season precipitation. You see the same data that we, at the driest plots the dried years had the highest rain use efficiency. Here is the shrub biomass over total. So how much we started with sort of a 50-50, and you see that as the shrubs dominated, the rain use efficiency increased. And so here, sort of the end of my, the part of we are in the midpoint of the talk, sort of wrapping up what happened with amount of precipitation. The first one is that it looks to me that this data reject the first hypothesis that there was no time effect. There was an effect of time on the ecosystem response, and there was a threshold. There was around 8 years. And so what happens nope, not 8 years. 9, okay. Between 8 to 9 years, there was some sort of a threshold. And the interesting for me is that is telling us that we cannot predict the effect of precipitation effects based on our understanding of pulses. With 1 year, 2 year experiment, we wouldn't have any idea of all these things that I've told you. What it makes it very interesting, because I don't know what is going to happen in the future, but it's a good message for our funding agencies that funding long-term experiments is essential. It's impossible to predict the future of climate, the impact of climate change by doing short-term experiments. And I don't know how Israeli science is funded, but the US typical grants last 3 years. So you are, in the best case scenario, if you're all ready to go, you can have a 3-year experiment, and then you are done. And then you run out of money. So that is sort of highlighting how important are long-term experiments, how different are the results of short-term experimentation versus long-term experimentation. The second one is about the asymmetry. It looks like the absolute magnitude of change was very different for increases in precipitation and decreases in precipitation. And the corollary of that is that we cannot predict the effects of drought based on experiment increase of irrigation or vice versa. So if we want to know what happened with drought, we need to do experiment with drought, but there are a lot of irrigation experiments around the world, but they are telling us a different story. Keep us employed. That's good. And the third thing is that there's differential responses among different groups. And I think by now you fully understand how different grasses and shrubs responded of that. And so wrapping up this part of it is that the major conclusion is that drought negatively impacted grasses. That doesn't affect, what am I doing wrong?
Just want to make sure we're using the microphone because we're screaming through Zoom.
Oh, okay, good. I usually speak too loud. That's what they always tell me not.
For the Zoom.
Okay, so the next, so first, drought negative impact grasses that shouldn't be surprising anybody. And the second one is that saltwater under prolonged drought deepens and reduces evaporation, because once the water gets to the very deep, beyond 50, 60 centimeters, very little evaporation from the top. And that increases the rain use efficiency, increases productivity, and what I think this is my main message. My main message is that the effect of climate change, the direct effect of climate change as seen as drought, was reversed by the indirect effects of changes in species composition. So if we would have studied the effect of grasses, never get the effect in direct effect with the 50-50 shrub grasses change into a shrub-dominated that is much more rain use efficiency, and the total production is much higher. So after 15 years, the effect of drought disappeared because of the indirect effect through shrubs, through changes in species composition. Do I make sense? No? What? Yes. Then I what? Patchy, of course. Yeah, I think we've been rehearsing this before. So he and I sort of at coffee time said, can you ask that question so I can try? I'll try to answer next in my next slide. So now yes, I think I will. The second part of the talk is about changes in variability, and I sort of introduce that. I think introduced that with the idea that there's an increase in variability that we've observed, that models predict, and also give you sort of the anthropocentric example of why variability matters. So here, my questions are simpler. How does precipitation variability affect? And how does precipitation affect diversity? It's an attempt to address your question. How does precipitation variability affect change along gradients of mean annual precipitation? Trying to see how this affects, because you're right, this is, you saw one site, one place, how can we extrapolate? I don't know, I'm not answering I'm just reporting on our studies. So in order to do that, we used our same old rainout shelters that pump water into the irrigated plots in year 1. In year 2, we flip. So these plots that in the year 1 had irrigation in the year 2 are going to have drought. And this one is going to have, that had drought, now it's going to have irrigation. So after an even number of years, all treatments are going to have the same mean, but different levels of variability. And so this is sort of I just took, this is an ongoing experiment, and this is the control. This is what happens when we, in this plot, we increase precipitation here, we decrease, we increase, we decrease. This is the opposite. These are the plots that we received. And we did that plus minus 50%, plus minus plus minus 80%. And what we found, I mean, this, I just look at even number of 8 years here, and you see this is mean annual the mean in all the treatments, the ambient, the plus minus 50%, the plus minus 80% in odd and even years. So you see that was pretty remarkable. The ambient was 127 millimeters, and the maximum was 128, and the minimum was 126. So really all had the same mean. But the coefficient of variation, when the ambient was 48%, and we were able to enhance variability up to 110%. So this, we experimentally changed variability without changing the amount. So this is, we separated the two dimensions experimentally. And this is some of our results here. I have two sets of slides here. Here we have the 6-year interannual precipitation variability. This is the results of our experiment. And in the x-axis, we have primary production. And we see that there was a negative impact of increased variability on production. That is sort of what we all, with our mind tied to our heart, we expect. So increased variability is bad, and then we see that. And this is what happened with the grasses. The grasses decrease with increased variability. But this is what happened with our misbehaved shrubs. The misbehaved shrubs, they did increase their production with increase in variability. And then we have something mixed bag we call rare species that accounts for most of the biodiversity in molar fraction of the production. So why? Why they have this differential response? Why ecosystems respond to variability? Why shrubs respond different than grasses? And let me try to take 2 minutes of our time here to explain our thinking about the mechanism here. So if this is the normal, the dotted line is the normal distribution of precipitation, annual precipitation, and their normal conditions in the future, and the increased variability scenarios, what we have is the mean is going to be the same, but the frequency of the mean is going to go down, and it's going to have fatter tails. So they're going to be more extremes, correct? So, and this is how this is going to affect production. So if this is, we have here is precipitation, here we have frequency, I'm going to add a new line that is the precipitation production relationship. And I would like you to focus on the solid line. So that's something that I'm sure I can convince you. There's more precipitation, more production. And this is suggesting that the extremely wet years are going to be more it's going to be more production. Extremely dry years, it's going to have less production. And so the effect of fatter tails can have no effect on the mean production, because the extreme the extreme wet is going to be offset by the extreme dry, and vice versa, correct? But what happens if the relationship is curvilinear? and this is what is called the Jensen inequality. Then if there's not, so I invite you to look at the dotted line. So the dotted line has an concave up relationship, and therefore extreme wet years have has a big increase in production. The extreme dry years have a smaller one. So what is going to when it increases the frequency of extreme events, what happens with the mean? The mean goes up. But what happens if our system has the solid line? It's sort of arrives sort of a plateau, the relationship between precipitation and production. And then it's going to be the opposite. So the very wet years have a relatively small impact versus the very dry years. And therefore, increases in variability is going to have a negative impact on the average production. Yes? And, 5 minutes. But we started late, so we can. And here, voila, this is what happens. This is the total production of the system, and voila, the system has a curvilinear relationship. And the shrubs, and this is the grasses. The grasses are the ones who have a negative relationship between production and precipitation, and this has a curvilinear relationship. But this is the shrubs have a positive, and the shrubs has the production precipitation that is the opposite. So the rare species have a straight line. So what it's saying is that the relationship between production variability and production is related with the relationship, the shape of the relationship between precipitation and production. Did I say it right? And I'm going to, these are the effects of diversity, and I don't know if I have time, probably I'm going to skip that. And this is the structural equations of the effect of variability. And this is kind of very close to my heart, because this is the effect of variability of precipitation has a positive effect on functional diversity. And this is what you didn't see in the previous slide because I went through fast. What variability did is increase the diversity. And basically increases diversity because it reduces the abundance of the dominants. So you get more of the rare species. And that has a negative effect on the productivity of grasses. But what is really my favorite one is this very limited line here, that the diversity has effect on productivity. And this is what you probably remember, like 10 years ago, Tillman et al. Were always looking at the effect of biodiversity and effect on productivity. And we're seeing the same thing. The increase in variability increased diversity, and diversity increased prime production. Very small effect, but it's still there. And so she's making me go fast now. And then, so these are the conclusions on the second part, is that the interannual precipitation variability itself has a negative effect in this particular system. And the nonlinear response of production to precipitation explains the effect of variability on production. If it's a curvilinear up, it's going to have a positive effect of variability. If it plateaus, it's going to have a negative effect of variability. And so the proportion of shrub and grasses probably tells you the end of the story. So my last part is what is the generality of our results? And that's trying to address the question that you and I sort of rehearsed during the break. And so we did this data mining. We found 43 sites all over the world that had more than 10 years of prior production. And this is where the sites were located along the axis of mean annual temperature and precipitation, to show you that sort of it covers most of the parameter space. And this is a figure that takes 30 seconds to explain. This is the slope of the relationship between variability and production. And this is mean annual precipitation. And so what that means is that there is a threshold around, there's a change around 300 millimeters of mean annual precipitation. Locations that are drier than 300 millimeters of precipitation exhibit an increase in production with an increase in variability. Sites that are wetter than 300 millimeters, there's a decrease in production as a result of increase in variability. Yes? No? Okay. Do it again. So this is the slope. What? What? Yeah, that's this line of the slope of the relationship between variability and production. If the slope is 0 at 300 millimeters, that means there's no effect of variability on production. Thank you for this dialogue. So if the slope is positive, as you see here, there's more variability, more production. If the slope is negative, more variability, less production. And what is interesting is that there's a point around 300 millimeters in space. So sites that are below 300 millimeters exhibit increase in production with increase in variability. Yeah? In sites that are wetter, it's the opposite. And voila, this is the relationship between precipitation and production for sites that are drier sites. See, between 0 and 300 millimeters, there's a positive relationship between production and precipitation. So remember the mechanism that we talked 5 minutes ago? And the sites that are wetter have a plateau. And so these are data, and this is our imagination of how, I'll show you experiments, I'll show you observations, I'll show you data mining. I'm going to show you a little bit of modeling. We have a model here, an ecosystem model, and then we play with this. And then we run the model for all these sites in the United States, and we calculated we increased variability by 25%, 50%, and 75%. What it means, so if you think about the simple thing is that you have 100 years of rainfall data. So rainfall 1, you increase it by 25%, then next event reduce it by 25%. So at the end of the 100 years, the mean is the same, but you increase the variability. And you can do that in the model by 25, 50, or 75%. But we also change the scale. We can do event by event. We can do year by year. We can do it every 3 years, 6 years, 9 years, or 12 years. So 12 years means 12 years high, 12 years low, 12 years high, 12 years low. So at the end of the 100 years, all of them have the same precipitation. But the variability increase at different scales and at different amounts. And we look at a lot of things like transpiration, evaporation, percolation, things like that. And this is what we found. And this is, all the figures are going to be the same, and I'm going to go fast because she's going to get mad with me if I talk too long. And this is mean annual precipitation for all those sites. Each one is one different site. And this is in the x-axis, we have the number of wet days when the soil water potential is above -1 megapascals. And the controls are always the black, and I encourage you to look at the red line that is the plus 75% increase in variability. And so this is what we found. We found that there's a threshold around 380 millimeters. Is this 380 millimeters look similar to the 300 that we saw it? It's not by chance. So there is something happening around 300 millimeters. So sites below 380 millimeters increase the number of wet days, and sites above 300 millimeters decrease the number when we increase the variability in the model. Yes? Yes? And this is when we do it every year. Ah, I lost it. Good. Can you fix it?
Yeah.
Okay. So you see that the effect is the effect of 1 year. If I do it for 12 years, the effect is even more sharper. Thank you. And, oh, it's working now. And when we do this for transpiration, this is the intraannual, this is the 12 years. I'm just sparing you all the middle so you don't get too bored. And you see the same thing around 380 millimeters. So there's an increase in transpiration due to increase in variability in the very drought systems. In the wetter systems, that's the opposite. And this is what happens with percolation. There's an increase in percolation. There's no percolation in the dry sites for obvious reasons. And there's increase in percolation as an increase in variability. So this is our final take-home message, is that the scale of variability was more important than the rate of variability. So if we, in the model, if we do it instead of year to year, we do 1 year, or if we do 12 years wet, 12 years dry, it's become a much larger impact than if we just do 1 year wet and 1 year dry. That I thought, oh, wow, what kind of nice result. And then I went for a bike ride and I said, oh, that's pretty obvious. That you increase it's the difference between having 10 5-millimeter events on one 50-millimeter event. If you have a very, very wet year, then you're going to have a very much larger effect than 10 small events. So in synthesis, what we see is that below 380 millimeters, that seems to be kind of an interesting number, there's more variability, it's more salt water, and this agrees with the higher production, correct? And the sites that are above 300 millimeters has more variability, resulting in less available water. And why is that? So this is one of our simulations for one site in northern Colorado. And what we have here is the number of wet days, and this is depth, soil depth from zero, from the surface to minus 80 centimeters. The black line is the control. You see this site range around 300 millimeters, so water never goes deeper than 20 centimeters. But when these are different increases in variability, the red line is the every 3 years plus 75%. What we see here is a deepening of the soil profile. As you increase variability, the water happens deeper. And this is the cartoon of where the water losses occur as a function of mean annual precipitation. Though the drier soils, the drier ecosystems lose most of the waters through bare soil evaporation. Water never gets very deep. Yes. Done? Okay. and so the deepening of the soil profile increases the losses in wet locations and reduces in places that are relatively drier. And so the overall conclusion is that the response of drylands to changes in precipitation amounts depends on the duration. I sort of convince you that the droughts are different than the wet years. And what I think is most interesting to me is that the indirect effects of changes in species composition sort of overshadow the direct effects of climate change. And then that the response to precipitation variability, this issue of what happens below 380 is different than what happens above, and is the most important. So, and I'm done. Thank you. Thank you very much.
Thank you very much for this really intriguing talk. We'll have one question. So, one question, short question. Yes.
So I wonder if you add temperature as additional variable in your models, how it will affect your conclusion.
First, my simple response is I don't know. I didn't do temperature experiments. Temperature experiments are a different beast. But I can tell you in that first example, first figure of that paper with Greg Motor, that we at the beginning we look at SPI and changes throughout the last 100 years, and we found a direct effect of precipitation on production, but we didn't find an effect on temperature. But then we look in the, and this is kind of complicated, that we look at the century changes in precipitation and temperature for the US, and there was no trend in precipitation, but there was a trend in warming. But the trend in warming didn't have an effect on primary production. Why? Because there's very little interannual variability in temperature. So what made the relationship between precipitation and production significant is that you have a very broad range. So you have very wet years, very dry years. Temperatures very increased throughout the century, kind of a 1.5 degrees. That what do you expect? But we didn't see an effect on production because there was no much statistical power. There was no much variability from year to year. And that 1.5 was not enough to see a direct effect. We did see a significant effect of precipitation. I don't know if I explained this well. Did I? Yeah.
Okay, so really, I'm sorry we don't have time. So really, thank you very much, Professor Sala. Really, thank you very much. Thank you.